Okay, so on the platform side, the main components which we have are, and like I said, please keep asking questions. The ensemble layer, the OML layer, and the ZML layer. And the things they are responsible for, our ensemble layer is responsible for the basic hardware management. So things like adding, removing nodes, and the basic clustering, which involves the use of HCD. The OML layer is responsible for managing OpenStack services. So basically starting, stopping these services, and health monitoring. Health monitoring and migration. So migration can happen for load balancing, like if you add a new node, it computes like what's the optimal placement of all the OpenStack services, and it can migrate it for that reason. Migration can also happen, we have some logic where if start of a service on a certain node is failing constantly, then we mark that node as bad for this service for some duration, and that can trigger a migration of a service to a different node. The ZML layer is responsible for what we call zero stack services. So these are the services used by zero stack software itself. So Redis, Cassandra, and Kairos are the three services. And the ZML layer does similar things for, like the OML layer does for OpenStack services. So yeah, that's a high level overview. Digging slightly deeper into the ensemble layer. And then there are some basic distributed libraries or utilities which all of them use. So we have a leadership election subsystem which is built on top of etcd. And we have a distributed wall which is again built on top of etcd. And this is used by all these layers. So you have a different election for ensemble going on, you have an election for OML going on, and election for ZML going on. Yeah, so
the ensemble layer, we built the ensemble layer, right?
what do you mean by we build?
I mean, did we code the
Yeah.
for the ensemble layer?
Yeah.
So one question is, when a system comes up, how is the election will happen at different level, right? Ensemble,
Sure.
and then can you just go through it?
So yeah, let's. So basically, we start off with a single node, right? And the first thing which we do is we do ensemble create. So that's how our software starts running. And as part of it, it starts etcd on this this node, and the ensemble layer gets started. And the ensemble layer starts off what it calls as applications on top of it. So OML and ZML are applications on top of the ensemble layer. They get information about the cluster from the ensemble layer. So they query the ensemble layer and it gives it information about which nodes are in the system. So these applications get started. Let's say OML, ZML. And ensemble also gets started. So as part of starting up these applications, start the leadership election subsystem. Right, so leadership election gets started, and since it's a single node system, the leader will end up being this this node itself. So the OML leader, in the code we call it OML master and ZML master, and the ensemble leader, they all end up on this node itself, right? But the election subsystem is now running, right? And So you have like a complete system in a single node system here.
So when first the leader election will happen in ensemble layer, and then on these applications when they are brought up by ensemble.
Yeah, I think the way it does is it ensemble does starts its own leader election. When that finishes successfully, again I'm not 100% about the flow. Maybe while the election is happening, it goes ahead and starts the apps as well. And when the applications start, they start their own leadership election. And so yeah, there are 3 leadership elections happening, but the code is refactored. So you have like a election monitor object, which so the code is the same for all of them. It's just that 3 different elections are in.
So here the election will actually have how the election actually happens. Who becomes the leader? What is the algorithm?
Yeah, so actually BVK knows all the details. I'll at a high level I know kind of what's happening. Basically, we rely on etcd. So etcd we use as a consistent KV store, and it has TTLs on keys as well.
Okay.
So the way it works is all the nodes which are participating in the election try to see if there's already a key there which has the leader for their category, right? If it exists, they just keep watching it, like watching it to, I think because it has a TTL, they keep watching it so that it doesn't get deleted.
Okay.
And if this doesn't exist, then they try to actually write their own information here to say I'm the leader. And yeah, I think the content of this key is information about who the leader is. So, so if this key disappears, then all the followers will notice it, and all of them will try to become the leader.
Candidate.
But yeah, become the leader basically.
Okay.
But etcd has this gives us atomic rights, right? So only one of them will succeed, and whichever succeeds, the other will start following it, monitoring this node to see that leader is stays there. So basically, etcd just gives us a consistent KV store, and then we have written a leadership election algorithm on top of it.
So in the process.
So basically, yeah, if there's like etcd connectivity issues, then sometimes what we see is what may happen is this. The existing leader is not able to refresh it, right? And if that refresh doesn't happen for some time, this node will get deleted, and the other nodes will try to become the leader.
So the key value store is accessed using the RPC mechanism, or how is it? So sometimes
There's a etcd client library, so we use that. Actually, we have another wrapper on top of the etcd client library, which is called Guru. So if you go to Guru,
yeah. So
yeah.
So Guru is only part of the ensemble, or it is part of leader election wherever it happens?
Yeah, so it's Guru is even a lower level library. It's so Guru is just on top of etcd client, which is used to access etcd, and leadership subsystem, since it's using etcd, it also uses the Guru library, and the distributed wall, since it's also over etcd, it's also using the Guru.
Could you explain a little bit more about Guru, like what exactly does? Yeah.
So it was written as a wrapper around etcd client, and I think it makes provides some APIs which are not natively available on etcd client,
Mm-hmm.
but it uses etcd client too. It's more of a convenience on top of etcd. So if you ask me what exactly does it provide on top of etcd client, I'll have to go back and take a look. I don't remember on top of, but yeah, that's
so etcd client is our like the.
And I think at some point the hope was if we replace etcd with something else, then Guru, the API exposed by Guru, can be the same.
Same. Correct.
But yeah, again, I don't know how true that is at this point. But yeah, that is the hope. Yeah, so that's the. So yeah, so this is a single node system. Everything is up. You can even go ahead and start OML and ZML here, and it will run on a single node system. But the interesting thing when you do a node add, right? So that is since it's a node addition, that's an RPC to the ensemble layer, and then ensemble layer goes ahead and does the node addition. I mean, digging deeper into it is. Basically, the node add is handled by the leader, because the leader is responsible for figuring out what are the nodes in the system. So that gets routed to the leader, but the leader is in this instance running on the same node itself, right? So the leader then sends an RPC to the new node which is being added, saying I'm adding you to my cluster, and it provides some information to the node which is being added. Things like what is your ZNet IP address, because the IP address management for the cluster is, the IP addresses are divvied out by the leader because it has the cluster view.
So there is no DHCP, it's just statically programs.
So I think some in virtual cluster at least the BREX IP addresses are assigned via DHCP, but the ZNet IP addresses, all that is under our control.
No, but we still give the range, right?
We give the range,
We give the range.
and then that range is divvied up by the leader.
Mhm.
It keeps track of which node has which IPs.
Mhm.
So that is, when it adds a new node, it gives a new IP which doesn't conflict with any other IPs in the system.
So these ZNet IPs are basically, these are assigned to the services running, are they the VIP or?
It's a virtual IP, virtual interface called the ZNet interface, and the idea is the services, zero stack services should use the ZNet interface. So HCD uses that.
Mhm.
I think Cassandra Redis also use that.
And the OML services, all this Nova and these are the like management.
They are divvied out from the management.
Management.
Yeah.
So only the
But that is not, Ensemble doesn't know about
know about
those.
that.
So the OML there.
So only Ensemble knows about the ZNet IPs. These
Mhm.
ZNet IPs are given to Redis, Cassandra, and Kairos.
So the IP is given to the ZNet interface and
Mhm.
Redis, Cassandra, and they use
take,
the
use
ZNet
the
interface
ZNet interface to get the, I mean,
to communicate with each other. Yeah, so once a node is added to the Ensemble layer, what happens
sorry,
is
one question. So these Cassandra, Redis, and Kairos, they will be running on all 4 nodes, right? If we have 4 node cluster,
Mhm.
right?
Mhm.
And each one will have different IP for
Mhm.
for that service
Mhm.
particularly, right?
Mhm.
And that will get from the ZNet IP
Range.
range.
So Ensemble has headed this node. What then happens is the OML layer is responsible for load balancing and management of open. And let's assume OpenStack has been created, right? So it's running on one node.
Mhm.
So the OML layer basically runs in a loop, and it kind of every time it first queries the Ensemble to figure out what the current hardware map is, like which are the nodes. And once it gets that, it computes a new plan, which is basically where should all the services be running given this hardware topology. And when you go from 1 to 2, the plan computation may return like some services need to be migrated to this new node. Once that happens, the OML starts migrating these services to that node.
So
And,
today, when we do plan computation, do we take care of things like these services should be running together, these services should be not running together or something?
we don't have affinity, anti-affinity, like we don't support that right now.
Okay. These are OML services, right?
So the thing which we support is each service can be assigned a certain weight,
Mm-hmm.
which is a static weight. It's not even based on runtime utilization. But if you know that these two are, from experience, they consume a lot of resources, you can give a high weight to both of them. So it's more likely when you go from 1 to 2, one of them will stay here, the other will move to this.
Okay.
So I think right now Nova, Neutron, MySQL, and RabbitMQ have high weights. So Nova and Neutron have high weights because they actually use a lot of resources. MySQL and RabbitMQ have high weights because we want to discourage their frequent migration, because that involves there's some risk because it doesn't involve data migration, but you have to detach and unmount and then.
And everybody is consuming RabbitMQ through and MySQL, right? So
That is
we
also
want to
true.
discuss.
Yeah. maybe we should add some better ways of doing that, except just this one static wait. But for now, that's what we do.
So the ZML, right? When ZML has its own leader in that case.
So again, just to complete this, the
Oh.
ZML is also running this loop. It queries the hardware topology from the ensemble layer and then does a plan computation. And if there are some migrations involved to achieve that plan, it undertakes that.
So the hardware scanning is done by the master, right? Or
The master.
everybody does it?
No, just the master.
And when a master fails, then master would be moved to a different node.
Yeah, so that's the leadership election will get triggered. So a new master will come up. As part of master initialization, it will read the distributed wall to figure out the OML master state, which can include actions taken by the previous master. But because the previous, so for example, any migration which happens, it's logged in the distributed wall, and the new master, when it comes up, it replaces the wall. So it knows the current plan, like where the services are supposed to run, and then it can take over from there. So we also do like checkpoints here. So till alpha, we would just keep writing to this wall. So every time there was a leadership change, this whole wall would be there. But now we kind of do frequent checkpoints. And so the whole state is checkpointed. So you just need to read that one checkpoint record to recover the state.
So in that checkpoint, when we read that checkpoint state, so first thing is, let's say when we have 10 records, right, in which we have, let's say, Cairo started and Cassandra started, Redis started, and after that we have a checkpoint. What would that checkpoint say?
So checkpoint is checkpoint of OML master state. So whatever actions happen, finally there is like this OML master structure, right? So there are some entries there. So one of the most important is what we call the current layout, which is a mapping of service to which node
Which
it's
node
running,
is service.
running on, or which nodes they are running on. So whenever like migration happens, we log it here, and while replaying it, we read that record and update the layout based on that. But when we do a checkpoint, we just write this layout in the checkpoint record. So you don't have to do like increments, you just read the whole layout.
Read the whole layout, and if says that
checkpoint.
on these 4 nodes, one node has no and neutron, other
Yeah,
had that
so you
is,
just get
so
that.
it will just start that. But in case of, I mean, we'll talk about ZML later, that's fine. Okay.
So yeah, that's so we rebalance based on topology. But the other thing the ZML and OML masters do is once they read the layout, and let's say topology hasn't changed, they query the service status, so they know which service is supposed to run on which node. So they then query the services status on that node. And if there is a error in that, they take remediation actions. So some things which can happen is a service is, you query a service and it actually says service status is down, right? And in which case we restart this, we go ahead and restart the service immediately. Another thing is you could get your service status is unknown, or there is a temporary glitch, so you couldn't get the status. So we have like a kind of a state machine built which says that there is a threshold, like if you have 3 successive unknown statuses where you don't know whether the service is up or down. So you don't immediately restart it, you wait for some time. If that threshold is crossed, you restart the service then. But if you actually are able to get the status and the status says it's down, then we don't wait, we immediately restart it.
One question about logs, right? I mean, every time like when OML starts, it says that cannot connect to maybe no assigning no virtual IP, assigning the virtual IP, something like that, right? It says all these error messages where you know, I mean, sometimes it's confusing, like for a new person like me, sometimes it's confusing that are these the now I'm able to understand that okay, it's starting of the service, it doesn't have the virtual
Yeah, I
IP.
think when we create the virtual interface, we always expect it to be there or something. So whenever we create it, we first say, and we log an error saying this interface does not exist, and
Yeah.
then we go ahead and create
Yeah,
it.
so those things, right? I mean, it's sometimes it get confusing because now you have bunch of these errors. It increases the log message. I mean, over the time now I understand that okay, these services started, so these log messages are okay. That these error messages are okay. But is there any plan to just scrub out these messages so that we only see relevant error messages that
Sure,
say
sure. And any such messages you come across, just let us know.
Yeah.
We'll take a look at it.
because I mean the log file becomes huge and it's hard to
Say which is the
say which
eventual
one.
error.
So I keep asking like, is this error fine?
Okay.
And when I report the bug, then it becomes even harder because people say no, this is not relevant. So we should have.
Yeah, just bring it to our notice. if
Okay.
you see something.
Okay, fine. So for that particular thing, right? I mean, are we going to do something about it that when it's about to bring the service up and say there is no virtual IP for that? I don't exactly remember the exact.
Let's see. I'll have to go and look at the code exactly.
Okay.
Because I think the error is printed out from a low level routine. So maybe in other contexts it makes sense to print that error message, but in this context where we
Mm-hmm.
know that most likely that interface is not going to
Correct.
be there, it doesn't make sense. But yeah, I'll at least take a look and see
Yeah.
what
Yeah. Okay.
what's the case.
I have a small question. In the whole framework, right, wherein the master and manager interaction is involved and we get the status, what all are the places wherein we hold a lock and do some operation? And what if, let's say, we are doing some operation on a process or a service, and if that service is doing something else, will that process wait till the other process becomes available?
So the communication,
If you plan to cover that somewhere later, that's fine.
no, actually, yeah, let's talk it now. Yeah, talk about it. So let's look at the OML. For ZML, it's similar. So the OML master communicates with on each node what you can think of as the slave, or we call OML manager is running. And right now OML master is mostly just single threaded. So that was to make locking and synchronization easier. So it kind of does everything in a single go routine. So what the OML master, so some of the RPCs which the manager respond to are like start service and stop service and query status. And each one of these RPCs actually acquires a lock in the OML manager, right? So if start service is happening on a node, then if you do a query status, that will get blocked. But the thing here is that all these RPCs are also issued by the master itself, right? So it doesn't happen that the master is, and since master is doing it in a single
Nobody
thread,
else would do query status on the same
Yeah.
node.
so it's not likely that when the start or stop are happening, the query status is also happening at the same time.
And are these the only three places wherein we hold the locks and do something?
These are the ones I can remember at like immediately, but I'll have to go back and take it. But I think yeah, for the most part, these are the.
So for a
And,
single node case, can you just explain how that will?
So in a single node, also like the OML master is running, and its communication with the manager is also through RPC. So this is a different go routine running here, and OML manager, like as in response to each one of these RPCs, a separate go routine is like RPC handler is triggered. So conceptually it's still kind of the same, even if they're running on the same node.
But then that problem will come when master is actually waiting on
Yeah,
manager,
that's
and
a-
manager is waiting on master.
That's a kind of a different issue. I mean, so the issue which Avignan is talking about is we have this logic where when OML manager comes up, it contacts it talks
To master to
to
do
the
some
master.
operation.
Actually, it just does a query on the master to get the current layout. So its purpose is when it comes up, it wants to see which are the services which I'm not supposed to be running and I'm actually running. And all the services which is not supposed to run, it then goes ahead and cleans them up. But if you have a single node system, what happens is when you reboot it, the master comes up and the master starts off. So actually, so let's say the master starts off by saying my state is unbalanced, right? And then will, then it starts off with a pessimistic assumption, and then it sees if all the services are balanced and fine, then it changes the state to say unbalanced. So the master is saying unbalanced. So it's, and let's say for example, actually some services are not running, so it will try to start those services, right? But in order to start those services, it needs to be able to talk to the OML manager, because the start and stop RPCs need to be handled by the manager. But the OML manager has not completely started yet, because initially it comes up and it queries the master for the plan, and it only accepts the plan if the plan status is balanced. So you are kind of in this loop where the manager is waiting for the master to become balanced, and the master is waiting for the manager to come up so that it can actually balance the services. So this happens in a single node system, so we are thinking of like a way to break the deadlock by the OML manager, if it sees that since it got the plan from the master, if it sees that there's just a single node in the system, then it shouldn't kind of keep waiting in this, it should just break out of the wait.
So we are handling it as a special case.
Mm-hmm.
Actually,
So this-
OML manager asks OML master for status. That call is a non-blocking call.
That is a non-blocking. Yeah.
The way to avoid the deadlock is to break the cycle.
Yeah.
So one RPC is always non-blocking. It never requires any locks. That is the status RPC. So idea is all OML manager to OML master RPCs must be non-blocking. They don't require any lock, and they must be by definition thread safe, whatever the state that they read, etc. They are mostly read-only operations. So that even though OML manager is doing an operation, it would immediately come back because it's a non-blocking. It's not waiting on the same lock again. But OML master, he will wait for some time and he will get the definitely get that.
Yeah. So in this case, the deadlock was not because of the RPCs as such. They were never getting deadlock in an RPC, but the higher level logic built on top, because the manager is waiting for the master to say the state is balanced, and the master is waiting for the manager to come up before it says the state is balanced. This can also happen in, like, if you reboot like all the nodes in the system, then there is a possibility you enter this situation where the manager is waiting for the master, and so there we have like a timeout here, like OML manager only waits for the master for some amount of time. So if you enter that situation, then it may get stuck for some time. But
And the election will always continue, right?
the election will continue. It's just that the master is waiting for the managers to come up, and the manager is waiting for the
So
master
this is not
to stay.
special to only one node system.
It's not special to one node, but it can even happen in a.
In node system.
But then we have this timeout here, after which the manager goes forward, and I'm thinking of reducing that timeout a little bit more. Right now it's 5 minutes. I think we can.
So I think this
Go
problem
lower as well.
can also happen. I mean, not a problem. I mean, this situation can arise when there is a master change, and then master actually is not yet in balanced state, probably replaying all, and then the managers are trying to stop and start services. Could that be a possibility when this, for a small window, this similar situation arises?
I think it. So the problem here is the manager is not responding to the master for a long time, right? So if you are in a situation where, which shouldn't happen normally, but if you are in a situation where, yeah, let's say leadership change happened and all managers are busy for a long time, then also the master will get stuck for some time waiting for the managers.
So, for example, in a 4 node.
But in this case, it was especially bad because the manager is also not coming up because of the master, right? It's not because of some other reason.
So in a 4 node cluster, so when we start, setting up the private cloud and all those stuff, first the cluster create request comes in.
So I think the sequence of cluster create happens, then all the 3 nodes are added.
Yeah.
Then we do a OML start, which starts, the OML master starts the OpenStack services.
Mhm. So this OML manager, so when we say start the OML OpenStack services, at that time OML manager starts. When does?
So the OML manager forwards the request to the OML master.
Mhm.
It's the responsibility of the master to then start the OpenStack services.
No, my question is, so let's say the cluster create happened, right?
Mhm.
The request came in, etcd started on one node. It said, okay,
Mhm.
you will be, this IP address will be the OML, ZML leader, this will be OML leader, this will be ensemble leader, right? So these 3 happen. So everybody is now, you have the master leader for that. So now after that ZML starts, right? ZML service start, all these Redis, Cassandra and Kairos, these start. Now after that OML starts, right? So in that OML start, OML manager starts, right, on all the.
So OML manager is started as soon as you do a cluster create. Or a cluster join. But
Okay.
it started, but it's not doing anything. It's just that, so OML managers are running, they're listening on RPC handlers, and when you issue a start, then it, so the OML manager running on one node will receive the start RPC, and then it will transparently forward that RPC to the master, and then the master will receive that RPC, and so actually the way the code is written is, when the manager also forwards the RPC, it is received by the manager on the master node, and then it knows that it has the master running, so it then invokes the the start RPC, OML start RPC on the leader object, the OML master object.
So in the AZ create request, OpenStack start services request, when the request comes to master, then it basically says that, okay, OML manager, you can start and all those.
So then it, the OML master receives this RPC, and let's say it wants to start a service on a certain node. It will send a start service RPC to the OML manager on that node, and then the service will get started on that node. But OML manager is just receiving stop RPC.
It's not asking for anything from
OML
OML
the master is orchestrating the whole bring up.
OML manager is just receiving the request and doing accordingly whatever
based
it
on
wants to.
whatever the master.
And in which case the OML manager is, so OML manager also reads the wall records to see like what's happening and all those stuff.
The OML manager
doesn't read that.
Yeah. So OML manager just has local state. We have local walls as well. I'm not sure what local wall state OML managers have. Ensemble managers, for example, when they get configured or join a cluster, then they store some information like the cluster UI in the local wall.
So who else reads the, like, you have the master who is reading the, writing the wall records and all the stuff, and you mentioned there is a token which gets deleted if the master is not updating it, and other people.
But also that's a different, so wall is a different entity, and this is used for leadership elections, so they are different things.
Oh, okay.
So this is being, the leadership election is always running, like all the nodes are constantly, all the OML manager instances are constantly looking at the OML election object to see if it's still live, if the master still holds it.
Okay. And once that token is gone, then they will start the leadership election, and then whosoever becomes master, then it's going to write the wall records and.
And there's some. So one thing is, let's say this was the leader previously, right? And the leadership election happened, this node became the leader.
Mm-hmm.
But if this node is partitioned away, this may still continue thinking I'm the leader and
Mm-hmm.
keep. So we have we use wall for kind of arbitrating between these two. So whenever some node becomes let's say OML master, it will actually forcibly try to write to the end of the distributed OML distributed wall to gain ownership of this wall, so that the other node is not able to write to it and change state.
I have a question. How do we create the distributed wall? Because if I understand raft correctly, in case of raft, there will only be one leader across the cluster. And in case of partitions, when the partitions merge, the only one node which has the highest election number will be the leader, and other guy will be forced to be the follower.
So
Isn't that the case?
we just use so we are building the wall at a higher layer than that. We just use the KV store capabilities that HCD gives us to construct a wall on HCD. So we are not really looking
In the
deeper into how HCD is doing things, right?
so the HCD cluster is different and our cluster is different. Is it the case?
Yeah, so for us, if HCD is running on 3 nodes, the OML master can be on a completely different node, right? It doesn't have to be on one of the nodes on which HCD is running. We just use HCD to. What HCD gives us is that, for example, the leadership view is not partitioned, right? Some side has a different view of.
So we still need HCD cluster to be working for our stuff.
Yeah, but the downside there is if you have let's say a 15 node cluster and just 3 node HCD, and if a partition happens and all 3 nodes are on one side and the other 12 nodes on different side, then all our stuff OML masters will only be running
Local
within
to
these
3
3.
nodes.
Yeah, it won't be our majority, it will be whoever
The
has the
other.
HCD majority. So we need to
So for our stuff to work correctly, we still depend on HCD cluster to work correctly, right? If there is actually a partition in HCD cluster itself, then there is a chance that our work might get overwritten with the other cluster.
It will not get overwritten, we'll end up being in the majority HCD partition. The OML master, the leadership elections, they will succeed in the. So if you have 3 node and 2 nodes are on one side of HCD and 1 node is on the other side, our leader will end up being on the side which has 2 HCDs.
Okay.
But the flip side is, the side which has 2 HCDs may have just 3 of our nodes and rest of our nodes are on the other side. So
Right.
And why we are, let's say, if we have 16 node cluster or 8 node cluster, why are we only using 3 nodes for the leadership election? Why not odd number or?
I think we can change that. So we have a way to reconfigure HCD, just like you saw yesterday, right? Auto adjusting HCD.
Yeah.
So we haven't thought about it. I mean, we haven't spent time figuring out when we have 16 nodes how many HCD instances we'll have, but we can definitely bump it up. We should probably also think about if you have 4 Z blocks, then the HCD instances should not all be in one Z block, something like that.
Yeah, because
Actually, on your question, ETCD is running, as a process-wise, it's running on all 16 nodes, but only 3 are the replicas. With 3 replicas, you support 1 node failure. Okay, and 3 are the only ones. If you are doing a key value write, only 3 nodes actually store it in that data set, in the disk. Now, if you run ETCD in 16 node mode, then any key value update in ETCD will go into 16 by 2. In fact, it will go into every node replica. You see the point? A write will succeed only if you write into.
Also, the replication factor becomes 16 in that case.
Yeah.
Yeah, so the thing is,
That's why you don't want it.
yeah, and the other issue is then it becomes very slow as well, because your writes will succeed only if once you write to 9 of them in a 16 nodes.
But can't we adjust the replication factor? Even though my cluster size is 16, success is guaranteed after, let's say, 5 nodes are written or something, or that is not configurable.
You need to have a majority, first of all. If you want to support false, you need to have a majority. So, any two overlapping sets that you take,
Mhm.
they should have a common entity so that
Mhm.
if other guys fail, that this guy has the latest, the common guy has the latest.
Mhm.
So that's why we pick three, and one node, it supports one node failure because any two in a three node cluster, you take any two, that's the majority.
Mhm.
Now if you say 16 node or 15 node,
Mhm.
and one guy writes in these three nodes, another guy writes up the conflicting update in these three nodes,
Mhm.
you have messed up
Different.
situation. You cannot guarantee consistency.
And if we have this 15 node HCD, then is the assumption true that the fault failure of multiple nodes, we can tolerate multiple failure
Yeah,
nodes?
yeah, there are plus sides. I mean, it's not just replication factor is a downside,
Mhm.
but that is an issue only if you are a data path guy. We are control path guy, so we can actually pretty much go with the approach where
Mhm.
ETCD is running on every guy.
Yeah, because if like in a 16 node cluster,
Except perhaps ETCD guys themselves haven't tested
Yeah,
ETCD on
that's
16 nodes.
another issue. That everybody uses 5 node replication
Yeah,
at max.
maximum.
That's all.
Yeah, I'm only thinking about the the hardware failure side of it, that if we have a couple or three nodes failure, let's say people put like 4 appliances in different racks or something, if one rack goes down, you have 4 node failure or something like that, then can we tolerate that if we have 15 this thing?
Design wise, all you need to do is increase your ETCD size.
Yes.
But practicality wise, most likely your write will suddenly become from 1 millisecond to 5 milliseconds or
Yes.
something because it's going across racks or whatnot.
Correct.
And we have
You
like
need to do a bunch of other stuff also.
we have like a star CLI command which you can use to reconfigure on which nodes ETCD is running. So I mean we need to test that more, but I think another thing we can probably do is like have a best practice, like if you have 3 racks, then reconfigure ETCD to have one instance
Yeah.
on each.
One of the test cases, if you guys get hands on 16 node cluster, is can we start 16 node cluster with these 3 guys as the
And
ETCD
then
nodes,
move ETCD.
and then move completely into different 3 guys.
Yeah.
You can add one guy and remove one guy, add one guy, remove one guy.
Yeah.
You can keep on moving it. That capability is there, but nobody tested it.
Yeah.
So that's a possibility.
I have a slightly different question. When there is an n node system for us, right? Why do we wait for somebody from the sky to say easy create start and then start all the services? Why can't, is there a possibility that whenever a guy join the cluster, at the end of that you just start the whole cluster itself?
I think because we wait for input, right? The management subnet and those ranges, we need an input from the UI. Because those IPs are then used to carve out
Okay.
IP ranges for services. And that is something we can't figure out ourselves. We need them to tell us.
Okay.
So another question is like, in case of any problem, how do we normally debug? Where all we should go and check, and what kind of logs?
So the most common thing I do is grep OML master, what the master is doing.
I mean, yesterday he spent like almost like 2-3 hours with me. I mean, just to make me understand, what's happening and what's not. I mean, we should have a session where just talk about logs and how to debug and all this stuff.
Or maybe the next time you get stuck on a bug, grab hold of me. And right now we are small enough,
Yeah.
and then you can train the next ones who come.
Yeah.
I have a so let's say in those cases, right? Let's say if we get stuck in some cluster and something, is there a utility which will print what all are the I don't know whether it's useful or not, but from last checkpoint to current state, just print what is happening on the master.
I mean, the way I do it as it is look at the log, right?
Look at the
grep
log.
OML master, it will tell you all that. Yeah, maybe over time we can add more, but for now that's. Another thing sometimes happens is etcd starts, HCD is very sensitive to network flips, and you will see a lot of HCD warnings. At that point, just do a ping on all the ZNet IPs from all the nodes and see if there's some packet loss. Somehow it's very sensitive to packet losses.
So are there,
And
I mean,
the consequence of that is leadership elections start getting triggered a lot.
So is there any configurable timeout that HCD cluster can have?
It has some timeouts for, and I did change that. I'll have to take a look again.
Because let's say election triggers during the execute step and then there is no way, right? Our execute
So there are
is
two
in phase.
timeouts, like HCD internally, its Raft algorithm has some timeouts which you can, like, when you start HCD, you can give different timeouts for how soon it detects something is bad. And then we have our own election timeouts, which is, what is the TTL for this node?
Wall.
Not for, this is the key being used for elections. So what is the TTL, like how soon, for how long can it survive without any updates? So I think, yeah, so I think it's set pretty high, like it's close to 15 seconds or something right now, but even then, leadership elections get triggered.
so all this communication across ensemble happens on 10,000 port, that RPC?
RPCs happen there, but yeah.
So, I mean, the
Even
HCD
for the
cluster is
OML
also on
and,
that?
even for OML and ZML, it's the
Everything.
same. I think it's the same HTTP endpoint, is just that all these objects.
Routes are different.
Yeah, they register a different handler.
On that point, unbalanced, I just looked at the code. If we are going to support one node failure, we should have a definition for what is the balanced state when there is one node failure based on current FTL. In a single node case, we don't support any zero failures basically. We don't support anything. So it should immediately say balanced on the zero node case. If there are 3 nodes in the cluster and one node is down, it should still say that okay, one node is down, I don't care, but rest of the machines are actually have all the OpenStack services that are necessary, so it is balanced. Yes, that logic is not there. That's why we see that all those live log kind of scenarios.
So as long as all the services are up, it should say even if a node is down. But in a single node system, maybe even the services won't be.
We should actually, based on the FTL, we should make the decision. Because you may say OpenStack services are running, but Ceph monitors, 2 monitors are down, say Ceph 2 monitors, nothing will run in the system.
Maybe we need another, because I think the balanced flag is used in tests to figure out can we now start issuing OpenStack commands. So it assumes if it is balanced, then OpenStack is available.
Not only there, in fact, OML manager, when it does start function, it actually waits for balance flag to become true when it queries the master state. And in the code, that balance calculation is wrong because it's not, if one node is down, then it doesn't even work. It never says balanced is true. So.
Okay, so can you actually also talk about the wall and the structure and how to use?
Okay, wall related story. This is a totally high level system. Wall would be a little bit deeper, like on specific component of the system. Basically, we use wall everywhere. Where is the okay? We have OML manager, we have OML master, we have ensemble, we have leader. Okay. The difference between these guys is basically ensemble is a node local entity. OML manager is a node local entity. Leader is a moving entity. it can move from one node to another node, etc. Same OML master is a moving entity. Okay, they have some in-memory state. What is the current plan? What is my IP address? What is my how many? For example, this component. This is ensemble component total. This one is OML component. Okay. There is a lot of state. Some state is node local state. Some state is cluster state. For example, what are the IPs that are free? What are the subnets that are manage? What is the management subnet? What is the tunnel subnet, etc. That information, how many of them, how many of the IPs, what IPs are actually already issued to the nodes, etc. This information falls into master state. What is my management subnet IP? What is my storage subnet IP? What is my tunnel subnet IP for that node? Falls into OML manager state. Similarly, here, leader has who are the nodes in the cluster, how many nodes are there in the cluster, which node, what nodes are etcd nodes, and what is the znet subnet znet subnet belongs to ensemble, and management tunnel and the other subnets belong to OML. Okay, what is the znet subnet and how many IPs are already issued out of them? Okay, this information belongs to leader. And ensemble has this information saying that what is my znet IP, what is my etcd IP, and am I a etcd node or not? What are the peers that I know? And this kind of, what is my public key, what is my private key, public key usually. What is my UUID, which node am I part of, which cluster am I part of? For example, there can be multiple clusters in the same data center, same network. This node is part of only one cluster. What is that UUID of that cluster? This leader has what is the cluster UUID that leader represents. This information, and if you look at it implementation wise, this is going a little deeper into how you get this working. Usually you have some kind of structure with all these fields, what is like management IP, UUID, etc. This is basically all objects of this are in-memory objects. This is the state, and it is running in memory, and if the process dies because of any reason, the state is gone. If you just set a variable, how do you make this state persistent? One way to do it is just store it in disk. Okay, you have disk say, and you store it in disk. Anytime you are changing some number, say for example version is 1. Every time you change this value, you again go and update the in-memory disk. So if you are storing this structure, this state in a file, every time you are actually changing any value, any state, you have to go and create a new file and overwrite and atomically change the old file using some kind of rename. Rename is the only atomic operation that you can do. This is one way of ensuring that your in-memory state and is persistent. Every time you die, you actually read whatever is there in the file and you will get it. But this one is very costly operation. You actually create a file every time you change. You have say some counter or number of RPCs or whatever. Every time it changes, you are actually creating a file and moving it. You are making multiple open, write and close and then flush and rename. That's not acceptable.
Yeah.
So what people do, if that is not acceptable, for some cases probably it is acceptable because the change happens only once in say 1 minute. Such kind of state it is okay, but not for state which can change based on RPCs or at any bigger rate. Okay. Now we will see we use val for storing this state, so that every time you are changing some entry, say for example UUID entry is changed for some reason, you actually write a val record, okay, and then change your state. Now what is the cost? Val is an object that is opened once, and all these records that you are writing in the val are actually appends. So you are actually doing one write for every one change that you are going to do. If you are doing batch of changes also, then you can actually batch all the changes that you are doing into one write and do it. And when you die, you first go and read the wall and read the records, and based on these records you can actually reconstruct the state. Say for example you have your state has S0, which is nothing, all fields are empty or 0. Now every change that you are doing creates a different state. You know, S1, this is the change that you are doing, C0. Then you write C0 in your wall. Okay, and you move to you change in memory data structure saying that hey, now I am at S1. Again, here you do C1 and you are S2. And then you are going to write C1 in the append. You are doing only appends. Okay. This is the minimum you should be able to do. Now at any point you die, you know, C3. Okay, C2. If you die, the way you recover is basically again you start with the structure which is empty, totally empty, all zeros, and then that means here, and then you read this all the records and you apply one by one. C0 is the record that you applied, you read, right? So you actually do S0, C0 and you go to S1. Now again C1, S2 and C2 which is S3, which is where you died. So that's the basic logic. Simple to say, but it becomes a lot complex when you are implementing it, because say this operation is an RPC operation because of that which you are trying to change. You say that I am writing C0, I am going to do C0 and I am doing it. And as part of this operation, maybe you need to adjust an IP address on the system or whatever. You need to do some other operation also, not just changing the state. And that operation can fail. If operation fails, you will say to the client that, hey, operation failed, and your state did not change because operation did not succeed. But you already wrote a record saying that operation, I am doing this operation, now you failed. Then you will actually end up with C0 doing it, and you don't have idea that this operation failed, and you actually said false to the client. You did not take any operation, but record is already appended.
So we should remove the record also if we are not killed at that point.
Removing the record is tough.
Oh, okay.
So what we do, we actually say that, you know, if the operation failed, we actually say that, you know, we write a record saying the C1, in the C1 record we say that, hey, C0 failed.
Oh, okay.
Okay. So now system, you wrote C0 and you wrote C1 also. So in the recovery process it becomes a little bit more complex, saying that you cannot just read C0 and apply. You have to read the entire thing to figure out what are the things that are actually changed. And then based on that you need to figure out from where to where. It becomes more and more complex. But the idea is this. So what you are doing is you have an in-memory state, doesn't matter what the state is. It could be a map, it could be an integer, it could be whatever, any kind of state. Every time you're trying to do a change, you actually write it into the wall and do it. Now where is this wall implemented?
One question before that. So how the checkpoint actually comes into this whole change, sequence of changes? So it will be somewhere...
Okay, then let's talk about checkpoint. This is fine, you understood the basic logic here. Now, if you run your system for 1 month, there will be, let's assume there are 1 million entries. Okay, and your process crashed. You are going to read 1 million entries and then going to replay all 1 million entries to construct your state. That is going to take a long time. So the idea is, how do I cut this into, you know, say my recovery time should not be more than 5 minutes, say. Then you can actually say, I will take checkpoint for every 5 minutes. What is this checkpoint? Checkpoint is a different file. I mean, it can be an entry inside this also, but you want it to be a different file that contains full state of the system. of this memory. Okay, it could be in multiple records or it could be a single record, doesn't matter, based on the size of this. Sometimes this is in gigabytes also. Okay, we have no restrictions on what this kind of state. It's not just a struct. It could be a structure of, okay, lots of things. So in this checkpoint, what you do is, checkpoint is an operation where you freeze the system, you don't allow anything, and then make a dump of everything into a file, into a disk, and then release this, unfreeze the machine. Say, theoretically you can think of it like that. Okay. Logically you will get the same. In implementation wise, you don't want to freeze the system if it is, say, 1 gigabyte. Now you want to write 1 gigabyte into a file, and you are freezing the system for 1 gigabyte write time, 1 GB writing time, which can be long. But logically you are going to get that, you want to get that behavior. Okay. And in the checkpoint you will have, basically say, let's continue the case. You have checkpoint for every 5 minutes. Okay, C1, C2, let's call these C1, C2, C3, etc. Now how does recovery change? Recovery is now not just read this fellow and then enter it, replay it. Recovery is actually figure out which one is the latest checkpoint that you have. Okay, this is the latest checkpoint that I have. Okay, and it was written at this point. Okay, then there might be some, cx plus 1. Okay, first restore this into your in-memory state, and then apply these entries. That's how the checkpointing works, so that you don't need to do million entries, replay million entries. Okay. Of course, there are lots of complications again. This is what I explained is basically one operation is happening on the object at a time. But if object is multi-threaded, there can be multiple operations happening at a time. Okay. And sometimes some systems allow checkpoint to be taken while the operations are going on. Okay. So there are lots of implementation related complications, optimization related complications, but theoretically this is what you want. Now, where is this wall residing? Wall and checkpoints residing? If they are in the local disk, local file system, then you cannot, if this node goes down, you cannot read it, because this node disk went bad or this node became unavailable. Okay, so here what I told you earlier, OML master and leader, these are the moving entities. Whoever becomes the leader will actually start creating these services. Okay, if this node, for example, at time t0, this is node 1, node 0, and that guy has the leader and ensemble. So the leader is writing it into disk-based, it says wall, disk-based wall and disk-based, checkpoints. And this node goes down. Later election says that okay, you have node 2. With the ensemble. And this guy here, he won the election, so he wants to start the leader service, but he cannot create the state that previous leader has, because this node went down and he cannot access the disk of this guy. So if you are actually if you are trying to persist state of moving entities, then you cannot use local disk based walls. Whereas ensemble, for example, ensemble is not a moving entity, and OML manager is not a moving entity. For these guys, if that node goes down or the disk goes down, they are not going to come up. And that's okay. Whereas for leader, he should always run. He cannot store it in this. He needs to store in some reliable storage which is accessible from multiple machines, all machines in the cluster. That's where this etcd based cluster comes into the picture. etcd is basically a cluster that provides key value store based access, and it supports one node configurable number of node failures. So if ETCD is running on this guy and this guy, and let's assume there is one more guy, it doesn't matter. It doesn't give you file interface, but it gives you key value interface. Now you have a reliable key value interface. You can again construct this same wall semantics on top of key value store. The way you do it is basically, C0 will be like, you create name calling that, delta, let's call these as deltas and this as checkpoint. Delta C0 key has a value which is actually nothing but the record C0. And delta C1 has a value that belongs to C1. Delta C2 has a value that that is actually. So you actually create multiple keys with some prefix. For example, this belongs to leader 1, then leader directory. Inside leader directory you create these. And if you want to implement checkpoints, inside leader you create checkpoint C0, checkpoint C1, these, and their values are nothing but the states that you want to store in the files. Now the recovery is same again. The new leader comes up. Yeah, we will come, fine.
So each entity you write into the etcd is just a key and value.
Yeah.
How do you interpret that is totally up to you.
Yeah.
And sometimes we interpret at as a value, like wall entry. Otherwise we interpret at as a checkpoint, depending on what you try to do.
Yeah.
Okay.
I mean, yeah, it's all up to us.
Okay.
Now, if one node goes down, etcd still says that you can read my entries because etcd supports node failures. So now this leader, this new guy who becomes the leader, he tries to go and read etcd entries, and he does the same recovery on top of these things, and he reconstructs the state. But there is one slight difference between local disk based walls and etcd based walls. Here, leader election happened because I said node went down. Okay, maybe nodes actually got disconnected, the cable got disconnected or whatever. Or maybe cable did not get disconnected, but there is a partition in the system. This guy doesn't know that there is a partition in the system. He still thinks that he is the leader. This guy thinks that he is the leader. Okay. Now both are trying to write, for example, this guy is trying to do some operation, CPU intensive job or whatever, and he is not talking to anybody. He got an RPC and he wants to do some computation, and he did computation, half of it, and he wants to write a delta record saying that half is done or something like that. And he goes ahead and tries to write it into the etcd. And this guy goes ahead and tries to write it into it. He started brand new and he recovered, and he is also probably redoing the same operation, or he started some other operation. He also tries to do it into etc. Then it's a problem. Two guys are trying to write. Both of them think that, hey, I'm going to write delta cx plus 100, let's assume. Okay.
Oh, so they actually start with a little gap.
Yeah, it doesn't. We should not allow this condition.
Correct.
What we do this when you are doing this, key value store updates, you do them using compare and swap. One of the operations that etcd provides is compare and swap. It writes an entry only if that entry doesn't exist. If that entry exists already, then it fails.
Okay.
So all these wall-based operations inside etcd are based on compare and swap. So one of them will win. Okay, only one guy can do the compare and swap based operation if it is not exist. Okay, everybody is leaving. So we will go.
Okay, you can.
We want this guy to win, not this guy. You see what I mean?
Correct.
Only one of them will win is not a good thing, because sometimes what if this guy wins? We actually hit the issues where this guy wins, even though he lost the leadership. This new leader cannot do anything here because this guy won.
Okay.
So we need to make sure that this guy wins. So this guy in a repeated loop, he tries to write it somewhere even before he starts any recovery. If he doesn't win, he gives up his leadership. Somebody else becomes the leader.
Oh.
and he tries to write.
And this is after this guy actually has become the leader. He
He
tries to write.
won the election,
Won the election.
but did not recover the state.
Okay, at that point he is trying to write
So
something
that
in the wall.
other guy will die. Okay.
Okay.
Yeah, and then we will go on. We'll come back.